cell potential under non-standard conditions using the Nernst equation and an example with concentration cells. This is the Electrochemistry lecture series part 5. Alright, so last time we talked about the relationship between the standard free energy, the equilibrium constant, and the cell potential. And notice that all of these are related. The free energy is related to the equilibrium constant. We can also relate the free energy to the cell potential. So basically, if we have one of these three quantities, then we can calculate the other two. Also notice that we can use any of them, the standard free energy, the equilibrium constant, or the cell potential to determine whether a process or a reaction was spontaneous. Alright, so let's talk about the Nernst equation, because this gives us a way to calculate cell potentials under non-standard conditions. In other words, when the concentration is not 1 molar and the partial pressure is not 1 atmosphere. Now, what we're going to do is go through and basically derive the Nernst equation, show you where it comes from, and then we're going to use it in an example, and then we're going to apply it to a concentration cell and talk about what that is. Reminding ourselves the change in free energy can be calculated for non-standard conditions using this equation. And we saw this in the thermodynamics chapter. We saw the free energy under non-standard conditions is equal to that standard free energy plus a correction term, RT natural log of Q. And remember that Q is the reaction quotient. Now we're going to substitute our definitions for the cell potentials into our equation for delta G, and then we're going to solve for cell potential under non-standard conditions. Negative NF delta E cell, that's under non-standard conditions. Negative NF delta E not cell, so that's the cell potential under standard conditions, and then our correction term, RT natural log of Q. Now, when we divide this whole equation by negative NF, so divide each term by negative NF, then we're going to cancel out and have just the cell potential under non-standard conditions. That's going to be equal to the cell potential under standard conditions minus, again, this correction term, RT, so temperature in Kelvin, our gas constant, 8.314 joules per mole Kelvin, Faraday's constant multiplied by N, and remember N is the number of electrons transferred in the balanced reaction, and that's going to all be multiplied by the natural log of Q, which is the reaction quotient. So if we set the temperature to 25 degrees C, then we can multiply all of these constants together and get 0.02592 volts divided by N multiplied by the natural log of Q. This is the Nernst equation at 25 degrees C. Now I like to sometimes remind students about the meaning of Q. So remember that we can calculate the equilibrium constant by taking the products to their coefficient power, multiplying all those together, and then dividing it by reactants, each to their coefficient power, and that has to be at equilibrium. We can do the exact same thing when we're not at equilibrium, except then it's called the reaction quotient. So this equation here at the bottom is just showing you products over reactants, but it's not meant to be specific in any way. You'd get those specifics from the reaction, and we'll see how to do that in a second. So let's do an example. So we have an electrochemical cell that was set up using this reaction, which we'll talk about, and it's at 25 degrees C, so we can use our shortcut. Now, we have iron 2+ cations in solution, and notice that the concentration is 1.94 molar. That tells us right away we're going to have to use the Nernst equation. Go over here, it's going to react with cobalt metal, we're going to get iron metal and cobalt 2+ cations in the concentration of 0.15 molar. So again, use the Nernst equation. And what we want to know is whether the cell will run spontaneously. And we want to justify our answer with appropriate calculations. We'll see how to do that. So let's think about it. What equation do we need to use? So we've already foreshadowed that we need the Nernst equation because we're under non-standard conditions. The concentration is not 1 molar. Let's look at the half reactions and the standard reduction potentials. Remember, in the Nernst equation, we need the standard cell potential in order to do our calculation. And then we also need that value of N, the number of electrons transferred in the balanced chemical reaction. Using the Nernst equation, we've got that down. We know we're under non-standard conditions. So let's look at the half reactions. Let's look at what's going on in this reaction. So we have iron 2 plus cations, and they are reacting to iron metal. So iron 2 plus cations plus 2 electrons gives us iron metal. So that's the cathode or the reduction half reaction. So we're going to write that down, and then we're also going to write down the standard reduction potential. Let's look at cobalt. So we start off with cobalt metal, and we end up with cobalt cations. That's going to be the anode reaction. That's going to be the oxidation. So cobalt metal goes to cobalt 2 plus cations plus 2 electrons. And the standard reduction potential for that reaction is negative 0.28 volts. So negative 0.447 volts for the iron reaction. We get that from the chart. Negative 0.28 volts for the anode reaction, and we also get that from the chart. And looking at our reactions, we see that we have 2 electrons transferred in this reaction. So let's calculate the standard cell potential. We have everything that we need for that. So we're going to take the cell potential is equal to the standard reduction potential for the cathode minus the standard reduction potential for the anode, plugging in our values from the chart. Negative 0.447 minus negative 0.28, so that's going to make that term positive. We end up with negative 0.17 volts. Now, just looking at the standard cell potential, it's negative, and that tells us that this reaction is not spontaneous as written. So the standard cell potential for this cell would not be, it would not be a galvanic cell. It would not be spontaneous. So the next question, do those concentration differences change anything? So let's check that out. So what we need to do with that is plug in our values into the Nernst equation. And so let's go ahead and plug everything in. So negative 0.17 volts for our standard cell potential, 2 electrons transferred in the reaction, our constant divided by that, multiplied by the natural log of products, so that would be 0.15 molar cobalt 2 plus cations, divided by reactants, 1.94 molar for the iron 2 plus cations. And when we do that math, we're going to end up with negative 0.14 volts, which is still non-spontaneous. And here it is just showing the second term. This is the value that you get when you multiply all of this together. And it's going to be a positive term. And so that's how we end up with negative 0.14 volts, which is not spontaneous. Concentration cells. Now, in order to determine the cell potential for a concentration cell, you have to use the Nernst equation. Now, these are special cells in that both electrodes are made of the same material. That means they're both basically the same metal or whatever else is used. And the cell potential for the cell arises from that difference in concentration between the anode and the cathode compartments. So those ions are going to be different concentrations. Now, we're going to use the Nernst equation to calculate this cell potential. So I've written my, instead of Q, we have products over reactants, but this is actually Q. So here's our problem. We're going to determine the cell potential for this concentration cell, and it's written out in cell notation or cell diagram. Now remember, the anode is always on the left, so here's our anode, and our cathode is always on the right. So what goes on in the anode? Well, oxidation happens, of course. So we have zinc metal going to zinc 2 plus cations, and we have 0.1 molar of those plus 2 electrons are going to be produced in that. The standard reduction potential for this half reaction is negative 0.7618 volts, and we get that from the chart. Let's look at the cathode reaction. So now we have zinc 2 plus cations in 0.5 molar plus 2 electrons that actually came from the anode reaction, and we're going to get zinc metal in our cathode. And the standard reduction potential, of course, is the same because we're dealing with the same material. It's really important to get the overall reaction when you're dealing with a concentration cell, because that's going to tell you which concentration is the product and which is the reactant. And remember, that's important for calculating Q. So we're going to add these two equations together. We're going to cancel out the zinc metal and the 2 electrons on each side. Of course, the standard cell potential is going to be 0 because it's the same. 2 electrons are transferred in this process. So we end up going from zinc 2 plus at 0.5 molar to zinc 2 plus at 0.1 molar. So we are now ready to plug everything into the Nernst equation. So here's our overall reaction again, just repeated, our cell potential, and we're going to go ahead and plug everything in. 0 volts for the cell potential minus 0.02592 volts divided by 2 electrons transferred in the reaction, multiplied by the natural log of the product concentration, 0.1 molar, divided by the reactant concentration, and that's going to give us a cell potential of 0.021 volts. Now that is a spontaneous process because that cell potential is positive. So basically what happens, just so you can picture it, as the cell runs, the concentration of zinc 2 plus ions is going to increase in the anode compartment and it's going to decrease in the cathode compartment. Now once the cell potential overall reaches 0, the current is going to stop. Next up will be electrolytic cells, and that'll be the electrochemistry lecture part 6.